Welcome to section 6.4, day 2, another adventure in chapter 6. In fact, the last adventure in chapter 6. Applications of exponential growth and decay. Actually, we have done many applications before, like in Algebra 2. I don't know if you ever did them in pre-calc. But I did show you last lesson about the law of exponential change. Please note that again, we're going to actually use that in 3 fancy-dancy problems. The first one is all about half-life, the time required for half of the radioactive nuclei to decay. Now, some of you may know about this from some science class. I don't know which one, but we're going to talk about it now in terms of calculus. So this problem is page 354, example 5. It says that carbon-14 has a half-life of 5,700 years. Find the age of a sample where 10% of the radioactive nuclei originally present has decayed. Okay, so what we're going to do is we know that the half-life, T, is equal to 5,700 years. So what we're going to do is use that information to calculate a K value. Now, you can memorize this half-life equation if you want to. K is a rate constant, but I like to think of half-life like this equation right here, which again I've marked up. But the left-hand side is your final amount, a half. The initial amount is 1. It doesn't really matter what the quantities are, but the final amount is always half of the one you started with. So this is our exponential law of change equation, and we've plugged in information for a half-life. Now, if we know that the half-life is 5,700 years, in this equation up here, we can calculate T. So that is the first thing we're going to do. The given half-life allows you to calculate K for the equation. That's what we're going to do. All right, so 0.5 divided by 1 is just 0.5 equals, it's a 5, e to the k times 5,700. All right, so we know how to take the ln of both sides, true? So ln of 0.5 and ln of e to the blah, blah, blah is just equal to the blah, 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 which is k 5,700, because those cancel each other out, equals ln 0.5. All right, so if we take k and divide both sides by 5,700, we have ln of 0.5 over 5,700. All right, that gives us our k value, and we have a little k value here, negative 1.2 times 10 to the negative 4. That is our rate constant. Okay, now to go back to the original equation, we want to find the age of a sample in which 10% of the radioactive nuclei originally present has decayed. So again, age means we want to find T. We're going to use the same equation, but in a different way now. We're going to take K, use this value for K, and we're going to do Y equals Y0, e to the kt. We have a K, we want to find T, and we know that okay, I'm having a technical difficulty. I can't make my screen longer, but here goes anyway. We're going to take our K value. We know that the 10% of the nuclei originally present has decayed. Therefore, our final amount is 0.9, and we started with a 1 because 10% has decayed. E, and we have this K number, 1.2 times 10 to the negative 4 times T. We have to do some fancy ln's of both sides so that we can figure out what T is. So we have ln of 0.9, and this is a 1, by the way. If we take the ln of both sides here, we get negative 1.2 times 10 to the negative 4th times t, because the ln and the e both cancel out. So now we're going to divide both sides by negative 1.2 times 10 to the negative 4th, and that's going to equal our t. This number right here is t. And you can calculate that. And if you do calculate that, you get 866.4 years. So 866.4. And that's in years because of other parts of the problem. And by other parts of the problem, I mean that it says the half-life was 5,700 years, so we know this unit is also in years. Our next problem is one about bacteria growth, page 357, number 24. In case I run into this problem again, I'm going to squeeze this stuff up a little bit. Board problems. Okay, a colony of bacteria is grown under ideal conditions in a lab so that the population increases exponentially with time. At the end of 3 hours, there are 10,000. At the end of 5 hours, there are 40,000. How many bacteria were present initially? All right, so if we use this equation, what we're going to have to do is, in order to figure out y sub 0, we're going to have to actually make two equations. This is fun. This is solving two equations. Our hours are going to be the time part. This is going to be y, which is the ending amounts. This is t, and we're going to use these to find y sub 0. So, ready? Let's make two equations. 10,000 equals y sub 0 e to the negative k. And time is 3. And this is 40,000 equals y sub 0 e to the negative k times 5. Sorry, I don't know where this negative came from. This should be a positive. I don't know where that actually came from. So, I'm going to rewrite this. It's just k to the 5th and k to the 3rd. Now, what we're going to do with these two equations is divide them. I don't know if you remember doing this in Algebra 2, but I do. Okay, so 1/4 equals, these y sub 0's cancel out. We're going to end up calculating k. Remember, e to the k times 3 minus k times 5 is e to the k negative 2k. Okay? 3k's minus 5k's give us negative 2k's. We're subtracting exponents. All right, in order to find k, we take ln of 1/4 equals ln of e to the negative 2k. And remember, the e's and the ln's cancel out. They're inverse operations. We end up with negative 2k's over here equals ln of 1/4. And we divide both sides by a negative 2. And that is our k value. Now, that's not really what we were looking for, though. We're looking for y sub 0. So we're going to go back to either one of our equations that we started with. And we're going to take k equals ln of 1/4 over negative 2. If you want to make this into a number, that's okay. Times, in this case, it was 3. All right. And if you do this calculation, because this is just a number, and then divide that number into 1,000, you should get y sub 0 equals 1,250 bacteria. I don't know how to spell that. Bacteria or something. Some plural of that. Okay, check that answer to be sure. Dating Crater Lake. We're not talking about going on a date here. we're talking about figuring out how old Crater Lake is. Crater Lake is in Oregon. If you remind me, I'll show you a little video of it. It's very short, but it's interesting. Okay, charcoal from a tree killed in a volcanic eruption that formed Crater Lake in Oregon contained 44.5% of the carbon-14 found in living matter. How old is Crater Lake? Well, let's start with the same equation we start with everywhere. If you go back to the very first example we did, that also was on carbon-14. And so the K value for carbon-14 is 1.2 times 10 to the negative fourth. So take that number, and what we're going to do is 44.5 is the ending value. Actually, it would be 0.44. Sorry, it's a percent. 0.445, and the beginning amount is 1. E, here's our K, negative 1.2 times 10 to the negative fourth, and we want to find how old Crater Lake is, so we want to find T. So take 0.445, divide by this, E to the negative 1.2 to the fourth, that'll all cancel out, and divide it over here. How old is Crater Lake, you might ask? Well, if you put this in your trusty calculator, you'll find out that Crater Lake is, oh gosh, I can't read my own writing. I think it's 6,747 years old. Please check that number. It might be 6147. Just to be sure. Signing out for section 6.4, day 2. Yahoo!